Hi students, I'm just going to briefly talk a little bit about activity 2, which we didn't get to discuss during the lecture. So this is a concept on tautomerism, which is not explicitly in your curriculum, but over in Hwa Chong we thought that it is a very good idea to just introduce it to all of you. It can help in mechanism drawing, it can help you to look at things from a different perspective. And for those of you doing biology, you know that your four bases, A, C, T, G, they exist in some form of tautomer. Yeah, so it will help you to improve your understanding on quite a number of concepts. So first of all, this particular functional group here is known as a ketone. Yep. So a ketone actually exists in two forms. You can have an enol form where there's a swap in position of the H. So instead of the carbon being bonded to the H, now you have the oxygen bonded to the H. Okay. Now it is very easy for a lot of you to think that to convert from the keto form to the enol form, you simply connect them through this particular arrow pushing. Okay, which let me say once and for all is actually not correct. So many people will think that the arrow pushing looks like this. The pi bond breaks to grab the H, and then the CH sigma bond breaks to form the CC double bond. Now it doesn't go this way most of the time. Okay, if you actually move on higher level to do more chemistry, you realize that this kind of arrow pushing is forbidden. But we wouldn't go into details. Okay, so without actually making things a little bit complicated, let us just emphasize that for tautomerism to occur, you need to have the necessary condition. So it's actually either acidic or alkaline condition. Okay, so maybe just let me illustrate a little bit on the left hand side. In acidic condition, the first thing that will happen is your ketone will be protonated. Okay, and then in the process, you will get a protonated ketone. Okay, and in this case, after it is being protonated, then alpha hydrogen will be lost. So it will be lost as a H plus, and in this way it regenerates the H plus. So when the CH bond breaks, the pi bond now breaks towards the oxygen, which is the electron sink. Okay, and in the process, you form the ketone. All right, yeah. So keto-enol tautomerization could actually be accelerated, or rather, it could be helped or made possible in the presence of an acid. Okay, what about in a basic medium? Okay, so I'm going to illustrate to you. Okay, so in a basic medium, what's going to happen is that because your alpha hydrogen is acidic in the presence of a base, it is likely to be deprotonated, and then the pi bond will break, I mean the sigma bond will break to form the pi bond, and then the CO pi bond will break towards the oxygen. And then in this way, you're going to get the conjugate base of the enol. This is known as an enolate. Okay, an enolate. If you protonate the enolate, you will get the enol. Okay, but generally in basic forms, you don't really get the enol, but you get the enolate more often than not. Okay, so this is just a very short introduction to the keto-enol tautomerization. So they do not just happen without the presence of acid or bases. Okay, I mean they do happen if there are other factors stabilizing their formation. So for example, let me just find some space. Okay, so for example, this particular system, I have a keto group here and another keto group here. So there's two ketone flanked by a CH2 in the middle, right? Now, this particular molecule, right, the most stabilized form is actually one of the keto becoming an enol. The reason is it can be stabilized through inter or rather intramolecular hydrogen bonding, okay, between this O and this H. So delta plus, delta minus. Okay, so the presence of intramolecular hydrogen bonding can actually help to stabilize an enol form. Okay, now there could be other factors such as, for example, phenol. You know that phenol, you're going to learn under alcohol, is actually the enol form of this particular ketone. However, the phenol form dominates. Why? Because your 6-member ring is now aromatic. Okay, yeah, it's not a benzene ring. Okay, as compared to this. Okay, so the enol form will usually dominate if there are other stabilizing factors. Okay, so this is something that you might want to take note of. Okay, as to the rest of the exercise, I don't think I need to go into details because they are being shown in the answer scheme uploaded, or in the key answer key uploaded for you to take a look. Okay, but maybe just let me emphasize on one thing. Is there a quick way to know which form is more stable? So for example, we look at this very simple molecule, which is an amide. Okay, you're going to learn it under carboxylic acid derivative. This is known as an amide. So the other two potential tautomer, one of them will look like this. Okay, so instead of C11O, I have C11C and then NH2. Okay, and then the other tautomer will look like this. Instead of C11O, I have a C double bond N. Okay, and then OH. Are we able to tell straight away which is more stable? Of course, this seems to be a relatively dumb question because you know that amides is definitely more stable. Yeah, but remember this, this is a preconceived knowledge you have, right? Because those of you doing bio, you know that, you know, like amide or peptide uh, tends to be the more stable form. But after you learn about tautomerization, you realize that there are actually two other forms that could exist, but they don't exist in great amount. Why is that the case? Okay, that is the case because a simple way to look at it is amongst all the C double bond, CO double bond is way stronger as compared to CN double bond and as compared to CC double bond. So in terms of thermodynamics, solely based on thermodynamics consideration, okay, this form is definitely the most stable. Okay, so this is just a quick way for you to check which tautomer is more stable. Okay, then you can get the rest of the answers from the key upload.